So we are going to talk about perimeters and areas of similar figures. Do we remember, it's been a minute, do we remember what similar figures are? They have two things. Do you remember the two things, Dahlia? The angles are congruent. The sides, we know that they're not congruent. We call them proportional. Okay, so that's what similar means. Angles are congruent, sides are proportional. Essentially, what we're going to be looking at is the same shape, but just in different sizes. And we're going to be comparing them. Now, basically, we have one big theorem we're going to use here. I'm going to color code this a little bit. And I'm going to talk about two different kinds of dimensions. First, the similarity ratio of two similar figures. When I say similarity ratio, I am talking about the ratio of its side lengths. We measure the length of something, like imagine with a ruler or a tape measure, you're measuring them in centimeters over centimeters, inches over inches, feet over feet, something like that, right? If I can erase this, I don't know why it's being weird. Let's say that ratio, we'll call it A over B. And that's just the ratio of side lengths. Then I have two things that are true. The ratio of their perimeters is exactly the same as the ratio of their side lengths. So again, A over B. Perimeter is also measured just like with a tape measure, straight line distance. That's centimeters over centimeters, inches over inches, feet over feet. Pretty standard. However, if I'm talking about the ratio of those same shapes areas, then my ratio changes a little bit. It's no longer just A over B, it's A squared over B squared. So I take my ratio and I squared both of those pieces. Now, this will be a little bit familiar if you remember those tiling problems, and I had a long spiel about why we can't take like 576 inches squared and then divide that by 12 to figure out how many feet squared. It's because of this rule. I can't divide area ratios by the same thing as similarity ratios, side length ratios, because they're not the same ratio. So, our units, when we measure area, this is going to come in handy to make sure that we have our units correct. Centimeters squared over centimeters squared, inches squared over inches squared, feet squared over feet squared. We're going to make sure that in our ratios, we are always having the same correct units as we go. So this is a little bit of like a discovery and exploration. I'm only going to make us do one of these. The first thing we're going to do is find the perimeter and the area of each one of these shapes. And then we're going to start comparing them. So for the smaller shape, my perimeter, 2 plus 4 plus 2 plus 4 gives me 12 units as my perimeter. And then the area of this shape, 2 times 4, is 8. Same thing with my larger shape. My perimeter is 3 plus 6 plus 3 plus 6, which is 18. And then the area of this shape, 3 times 6, is also 18. Good there? Okay. So, when I see the word similarity ratio, I'm thinking about the side lengths. So I'm going to pick two corresponding sides and figure out what the ratio is. I'm already assuming that these are similar, so I don't have to worry that they're not. I'm going to assume I'm going to pick two corresponding sides. Let's pick 2 and 3. The ratio of the sides then is 2 over 3. You can see that if you look at the bases too. 4 over 6, that reduces to the same ratio, 2 over 3. Now let's take the ratio of the two perimeters. We found the perimeters in the first step. 12 over 18. if I reduce this by this rule I talked about up here, it should come out to the same number as the similarity ratio for my sides, which 12/18, we can divide both of those by 6, and we do, in fact, get 2/3. I'm going to put a shocked face because everybody is just shocked by this information, right? Not like I just told you 5 minutes ago. We're going to do the same thing for the areas. I'm going to take my two areas, 8, in a different color, 8/18. That reduces, I can divide both of those things by 2. It reduces to 4/9. Now think about how I got 4/9. Think about my similarity ratio and the rule I just taught you. 4/9 is the same thing as 2 squared over 3 squared, which is my similarity ratio squared. And once again, shock and awe. We are all shocked. Yes? That's where this rule is coming from, essentially. I don't think it's necessary for us to do the rest of these exploration ones. Are we good to move on to the word problems? Okay, fantastic. The figure in each pair are similar. Again, we are already under the assumption that these are similar. We don't have to do any extra work to prove that. We did that already a few units ago. The area of one of the figures is given. We are trying to find the area of the other to the nearest whole number. The important part of this lesson that we are going to do is proportions. In your work, I want to see your proportion. However, we cannot just go straight from the ratio of the sides into a proportion with the areas because the ratio of the sides is not the same as the ratio of the areas. So we're going to do a couple steps. I'm going to start step 1 by writing the ratio of my side lengths. And I'm going to keep color coding this. Number 1, the ratio of my side lengths. Doesn't really matter if you want to do 8/2 or 2/8. I'm going to do 2/8 because I think it looks pretty. There's a ratio of my side lengths. I'm going to simplify these to get 1/4. And I really like keeping those units with these numbers to make sure that I have the correct ratios. So 1/4, ratio of my sides. My second step is to now figure out the ratio of my areas. And to do so, I'm going to square both of those numbers. So 1 squared is 1 inch squared. And then 4 squared is 16 inches squared. And this is the new ratio of the areas. Notice how my unit is now inches squared. Everybody good with that? The last step is the proportion. This is the step that I really want to see in your work. I'm going to take that new ratio of my areas, 1 inch squared over 16 inches squared, set it up into a proportion with this area that I already have. It's the area of the smaller shape is 96 inches squared, so it does matter where we put this. Make sure you're going to put it with the smaller piece. And then cross multiply. So this is 1x equals 96 times 16, or x equals, whatever 96 times 16 is, 1,536 inches squared. Let me blow this up a little bit. There you go. Any questions on that? We're going to do it again. Okay. Again, we're going to start off by writing the ratio of these side lengths. 6 centimeters over 15 centimeters. That's step 1. I'm going to simplify this if possible, which I can do here. I can divide both of these by 3, I believe, to get 2/5. And then, step 2, Now that I have the ratio of the sides, I need to figure out the ratio of the areas before I can put them into a ratio together. So 2 squared is 4 centimeters squared. 5 squared is 25 centimeters squared. So I'm going to take that ratio of my areas, 4 centimeters squared over 25 centimeters squared, and I'm going to put it into a proportion with the area of my larger shape, 2,025 centimeters squared. It's the larger shape, so obviously we want to put it down in the bottom with the larger piece. Everybody cool with that proportion? I'm going to cross multiply 25x equals 4 times 2025, which is 8,100. I'm going to divide by 25 and get that x equals 324 centimeters squared. Any questions on this? I'm not going too fast, right? We're good? Okay. There's only 3 more problems, so we're just going to get through them. The ratio of the dimensions of 2 similar pieces of window glass is 3 to 5. The smaller piece costs $2.50. What should be the cost of the larger piece? So the first thing that I see in this word problem, and this is very similar to the word problems you'll see on your homework, is that the ratio of the dimensions of 2 smaller pieces is 3 to 5. When you see that word dimensions, it's talking about side lengths. So I know that 3 to 5 is already the ratio of the sides. Now, when it says the smaller piece costs $2.50, that is being calculated by the area of the glass that you're purchasing. So $2.50 it has to do with the area. So in order to write the ratio with this dollar amount, I need to figure out the ratio of the areas, which once again, I'm not doing anything different. I'm squaring both of these pieces to get 9 over 25 is the ratio of my areas. Yes? Now, because I know that 250 is calculated based on the area of the smaller piece, I'm going to set 250 up into this proportion with the smaller piece being on top. That's it. That's all I got to do here. And then I'm going to cross multiply. This is 9x equals 2 times 250 is 62.5 divided by 9. X is $6.94 because that cost is calculated based on whatever the area of the larger piece is. And you will see a bunch of problems like this on the homework. It's exactly the same process. Good? Okay, now I'm going to do something a little bit weird. We got to lock in for these last two because this is a little different. In number 4, it says 2 similar trapezoids have areas 49 centimeters squared and 9 centimeters squared. Find the following. If the perimeter of the smaller trapezoid is 36 centimeters, find the perimeter of the larger trapezoid. So we are starting with both of the areas. And then we're being asked to find the perimeters. So I'm going to set up my area ratio first. And then I'm going to figure out the ratio of the sides because I go from areas to side lengths. So to get to the areas, we've been squaring these numbers. So the opposite of squaring something should be what? Caitlin? We're going to square root it. So we're going to square root both of those numbers to get 3 centimeters by 7 centimeters. And that is the ratio of the side lengths. By those rules I talked about on the last page, guess what? The ratio of the perimeters is the exact same as the ratio of the side lengths. So this is literally just going to go straight into my proportion with the ratio, the other perimeter that I have. The perimeter of the smaller trapezoid is 36 centimeters. And then my x. So 3x equals 36 times 7 gets me 252. Divide by 3. The larger perimeter is 84 centimeters. Everybody okay with that? Again, the last one is just a little bit different, so pay attention to this one. It's the same idea where we're going to start with the areas and then find the perimeters. So I'm not doing anything crazy here. I'm going to do 2,000, or sorry, I'm going to start with the smaller number. I like putting the smaller number on top. I'm going to do 135 feet squared, and I'm going to divide that by 2,535 feet squared. That's the ratio of my areas. Everybody good with that? What's the difference between this one and the last one? Dahlia? They're not perfect squares. And I don't want to deal with weird fractions and decimals when I put these into my proportion. So here's what we're going to do. I don't just want to simplify this down because I don't want to simplify this down all the way and then end up with numbers that still aren't perfect squares. So here's the process that I go through when I work on these problems. I'm going to take 135 and I'm going to start dividing that by perfect squares. So 135 divided by 4, 135 divided by 9. I'm going to go until I find something that works. And I do believe 135 is divisible by 9. Am I right? Let's look it up. I believe I have my calculator open. So not divisible by 4, but it should be divisible by 9. So 135 divided by 9 is 15. Everybody still with me? I don't want this number in my new ratio to be 15. I want this to be 9 feet squared. So I'm dividing by 15 to get 9 as my perfect square. That means I'm not going to divide 2,535 by 9. I need to divide it by the same thing, by 15. 2,535 divided by 15. We're going to hope this gets me a nice perfect square as well. 169 is a perfect square, so I know that I'm good to go here. And now that both of my numbers are perfect squares, now I can finally square root this. So the square root of 9 is 3. It's going to go right into my proportion. The square root of 169 is 13. No, 6. Yeah, 13. And then I fill in the rest of my proportion. The perimeter of the larger one is 142. And then I put my x in there. 13x equals 3 times 142. 426 divided by 13, 32.8. Did everybody kind of understand, though, my process for getting that fraction with the perfect squares? You look for what the perfect square is, and then you divide both of them by the other number, not by the perfect square. Good? Okay. Homework's in your packets.